Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we are going to discuss a topic, heat capacity equations. So our topic is heat capacity equations. Remember, first our TDS equations. Let me write them first. TDS is equal to CV dt plus T dou P by dou T at constant V dV. TDS is equal CV dt plus T dou P by dou T at constant V times dV. We name first, this is our first TDS equation. Then we have TDS equal to Cp dt minus T dou V by dou T at constant P dP. Let me name it second. This is our second TDS equation. Right? Now we equate these equations, right? Equating the first and second TDS equations, that is first and second, we get this is TDS equal to this, TDS equal to this thing, so we can equate them. So we get this Cp dt minus T dou by dou T at constant P dP. This is this result, second one, Cp dt minus T dou V by dou T at P dP is equal to Cv dt plus T dou P by dou T at constant V dV. Cv dt plus T dou P by dou T at constant V dV right? Solving for dt, we obtain solving for dt, we obtain. So our dt is equal now t dou p by dot t at constant v over cp minus cv, and you have dv here, then plus t dou v by dou t at constant p over cp minus cv times dt. Let me check it. You can check it as well. T dou p by dou t at constant v over cp minus cv times dv plus t times dou v by dou t at constant p dp over cp minus cv. But since temperature is taken as function of p and v, we can write dt as dou t by dou v at constant p dv plus dou t by dou p at constant v dp, right? Since we are considering temperature as function of pressure and volume, we can write dt equal to dou t by dou v at constant p dv plus dou t by dou p at constant v dp. Therefore, let me name these equations first. So second, this is my third, this is my fourth, right? So I can combine 3 and 4, or you can compare them. See here, this is dt equal this thing, this is dt equal this thing. Coefficient of dv here is, let me encircle it, this is the coefficient of dv. Here coefficient of dv is this. We can equate them. Likewise, use another color. I can equate this thing with dou t by dou p at constant p. So we write that comparing equations 3 and 4, that is these two equations, we get dou t by dou v at constant p is equal to t dou p by dou t at constant v over Cp minus Cv and dou t by dou p at constant v is equal to t dou v by dou t constant p over Cp minus Cv. Let me check it. Dou t by dou v at constant p is equal to t times dou p by dou t at constant v over Cp minus Cv. And here we have dou t by dou p at constant v is equal to t times dou v by dou t at constant p over Cp minus Cv. Now both of these equations, we name them both of the equations 5 yield the result that Cp minus Cv is equal to T dou V by dou T at P constant times dou P by dou T at constant volume, right? Cp minus Cv is equal to T times dou V by dou T at constant P times dou P by dou T at constant V. Right? So let me name it equation 6. Now dou P by dou T at constant V is equal to minus dou V by dou T constant P times dou P by dou V at constant T. How we obtain it? Remember the cyclic rule. Still refresh your memory. Remember, let me use this color now. Using dou xy dou y at z times dou y by dou z at constant x times dou z by dou x at constant y is equal to -1. Dou x by dou y at constant z times dou y by dou z at constant x times dou z by dou x at constant y is equal to -1. Using this is called cyclic rule. Instead of x we have p, instead of y we have v, and instead of z we have t. So instead of x, y, z we have pvt. So for pvt system we can write it dou p by dou t at constant v is equal to minus dou v by dou t at constant p times dou p by dou v at constant t. Using this thing, let me name it 7. Using equation 7 in equation 6 we get, that means we replace dou p by dou t at constant v in equation 6 using 7. So we get Cp minus Cv is equal to minus T dou V by dou T at constant P square times dou P by dou V at constant T. This is my equation 8. This is my 8. Cp minus Cv is equal to minus T dou V by dou T at constant P square times dou P by dou V at constant T. Let me encircle it. Now equation 8 is an important equation in thermodynamics. And it shows that first, since dou P by dou V at constant T is always negative, for all known substances, and dou V by dou T at constant P square must be positive. Then Cp minus Cv can never be negative, or Cp can never be less than Cv. It's important. I repeat, dou P by dou V at constant T is always negative for all known substances, and dou V by dou T at constant P square must be positive because it is a square. Then Cp minus Cv can never be negative because in this equation, this thing is always negative, this is always positive, and we have a negative here. So negative times that negative is positive. That means Cp minus Cv can never be negative, or Cp is always greater than Cv. It can't be less than Cv, right? This one conclusion. And remember, what is the meaning of dou P by dou V at T is always negative, right? That means at constant temperature, if you increase volume, pressure will drop, right? Second conclusion is as T approaches zero, Cp approaches Cv, or at absolute zero, the two heat capacities are equal. You can see if T approaches zero, this difference approaches zero. That means Cp approaches Cv, or at absolute zero, the two heat capacities are equal. Third thing, Cp is equal to Cv when dou V by dou T at constant P is zero. If this derivative is zero, then Cp minus Cv is zero, Cp is equal to Cv. When that happens, that means at constant pressure, by changing the temperature, volume will not change. That is the meaning of this derivative equal to zero. For example, at 4 degrees Celsius temperature, that is the temperature at which the density of water is a maximum, Cp is equal to Cv. right? I repeat, Cp is equal to Cv when dou V by dou T at constant pressure is 0. An example for that is 4 degrees Celsius temperature, the temperature at which the density of water is a maximum. Cp is equal to Cv for water. Now, laboratory measurements of the heat capacity of solids and liquids usually take place at constant pressure and for unit mass, and therefore data are reported in terms of specific heat, that is small cp. It would be extremely difficult to measure with any degree of accuracy the specific heat at constant volume small cv of solid or liquid because of thermal expansion. Now, values of cv specific heat at constant volume, however, must be known for purposes of comparison with theory. Now, the equation for the difference in the specific heats is very useful in calculating specific heat capacity at constant volume in terms of specific heat capacity at constant pressure and other measurable quantities. Now, to get the equation connecting these two things, that is specific heat capacity at constant pressure and specific heat capacity at constant volume with measurable quantities, we can get that equation. We know that volume expansivity is beta is equal to 1 over V times dou V by dou T at constant P and isothermal compressibility is you've already discussed it. Kappa is equal to minus 1 over V dou V by dou P at constant T. Using these, we can write using beta and kappa, we can write equation with the name 8. Equation 8 as Cp minus Cv is equal to T V times 1 over V dou V by dou T at constant P in square over minus 1 over V dou V by dou P at constant T. Remember, this small Cp is specific heat capacity at constant pressure, and this small Cv is specific heat capacity at constant volume. So it is heat capacity per unit mass, right? Let me check it. It's Tv 1 over V dou V by dou T at constant P square or minus 1 over V dou V by dou P at constant T. And this small v here is specific volume. Let me write. Small v is specific volume. That is volume per unit mass. So it will be actually actual volume V over mass of the substance. That is the meaning of specific volume per unit mass. So, or I can write small Cp minus small Cv, that is specific heat capacities I am considering, equal to P times T small v specific volume times beta square, that is expansivity square, over kappa, that is isothermal compressibility. This is an important equation. This is our equation 9. Yes. This is our equation 9. It is expressing now the specific heat capacity at constant pressure and specific heat capacity at constant volume, or I should say their difference in terms of the measurable quantities, pressure, temperature, specific volume, expansivity, and isothermal compressibility, right? Again, we will derive another result, right? At, you should take at constant entropy, S, from 2 TDS equations that are our 1 and 2. These are our 2 TDS equations, right? So at constant entropy, these left hand sides become 0. So we can write at constant entropy S from 2 TDS equations, that is equations 1 and 2, we obtain what we obtain. We obtain this. Cp dt is equal T do V by do T at P dP, right? And Cv dt minus T do P by do T at constant V dV. I write here Cp dt and I write subscript little s. That means entropy is constant. And in this dt, I also write subscript little s. Here I write dp subscript little s. Here I write dv subscript little s. It only indicates that entropy is held constant. So we have Cp dt s is equal T dou v by dou T at constant b dp little s subscript Cv dt subscript s is equal to minus T dou P by dou T at constant V dV subscript s. Let me name this 10 and 11. So dividing equation 10 by 11. Dividing equation 10 by equation 11, we get in jacket dt will go, here t will go, so we will get this Cp over Cv is equal to minus dou V by dou T constant P over dou P by dou T constant V times dou P by dou V at constant S. Right? Cp by Cv is equal to minus dou P by dou T at constant P is equal to dou P by dou V by dou T at constant P over dou P by dou T at constant V times dou P by dou V at constant S. Here we have simply converted the derivative dP by dV into partial derivative because entropy is held constant. We can do that. But the quantity in brackets is equal to minus dou V by dou P at constant T. Why this is equal to minus this thing? Because the cyclic rule, you can check that the quantity in brackets is equal to minus dou V by dou P at constant T. Therefore, Cp by Cv can be written as dou P by dou V constant S over dou by dou V at constant T. This is at constant T. Check it. It only simplify the things. So I'm writing the quantity in brackets is minus dou V by dou P at T. Therefore, Cp by Cv is equal to dou P by dou V at constant S over dou P by dou V at constant T. Let me name it. This is my 12. Then we define a quantity, the isentropic. The isentropic compressibility is defined as kappa S minus 1 over V dou V by dou P at S. Isentropic compressibility is defined this way. It is simply compressibility entropy at constant entropy, right? And as usual, the isothermal compressibility is given by kappa is equal to minus 1 over V dou V by dou P at constant T. We have therefore gamma, which is ratio of specific heat Cp by Cv, it will be equal to K by Ks. This is important equation what we have done. Let me name these equations. This is 12, this is 13, this is 14, and this is my 15. So what we have done, we have used 13 and 14 in 12. We write somewhere using 13 and 14 in 12. And we obtain this important result. You can write gamma, which is Cp by Cv equal to ratio of the compressibilities. Kappa being the isothermal compressibility and kappa S being the isentropic compressibility, right? let me move to, or, or I should stop here. We'll discuss the topic next time. This is all for today. Prepare your exams. Don't waste your time. And don't forget to subscribe my channel. Thank you. God bless you. Assalamu alaikum.